Hello, my name is Nathaniel. Today we are now going to do question 8 of step 2 2020. Now we have a very interesting question here. So in this question, f of x is a quartic polynomial. And do you know what a quartic polynomial shape is? It should usually look a bit like this or like this. And remember that these ends are about less curved than the quadratic. It's slightly straighter, which means if you graph x to the power of 4, it will look something like this. Sorry for the crooked, actually it's my terrible drawing. So you see, it's much straighter than your usual quadratic. But however, a quartic can have 3 turning points, as stated by the fundamental theorem of arithmetic, because then its derivative would be a cubic, and a cubic could have 3 real roots. So this is the type of quartic we are going to consider. Now it has 4 real roots, not A, B, and C. So what are we going to do? We are going to construct an x-axis here. So an x-axis which has the value 0, A, B, C. Now f of x is defined f of x being the integral. Now the fundamental theorem of calculus states that the derivative and integral are opposites, which means that you can take the integral on the derivative, you will get the function. Now, how is that going to be important? Well, you see, 0, A, B, C. Let us draw a normal quartic. It should look like this. Now, the area enclosed by the curve y is f of x, the x-axis between 0 and A is equal to that between B and C. Let us call this area. Okay, what's your favorite letter? Mine's Q. Let's call this Q, 2, and 2Q. Right, and explain why f of x must have the big F, the integral, must have this form. So, you see here, so the quartic should, when you draw the y-axis here, it will look something like this. So in you're going to calculate integral of 0, you must automatically have 0 here. Otherwise, you will have C, which would be some constant when you're starting from another area. So, and A, so when it's at A, the area will be negative Q. It's called signed area, mind you. A, B, and C. So this will go down to Q, go up to Q again, and then go down to 0, and looks a bit like this, because you see here, this is a positive area, this left side is a positive area, but since we are dealing with stuff on the left of 0, we have to negative it. Hence, it has double roots, as we call it, at 0 and C. Hence, it should have 1/5 x squared, x minus c squared. The 1/5 is from the integration of x to the power of 4 to get 1 over 5 x5. And then the other root, let's call it h, obviously. Now, I can already see where this is going to. We're going to prove h is equal to c over 2. How are we going to do this? We'll explain why f of b plus f of x is greater than or equal to 0. Now, as you can see here, in the area between 0 and A is Q, and the area between A and B is 2Q, and this implies that we are going to add Q to each of the areas. That means our shifted graph will look something like this. And you put the x-axis here. That is why f of b plus f of x is greater than or equal to 0. And the only way when this can equal 0 is when x equals to A, because A is where you call the valley or the minimum of the area, the signed area, which would equal negative Q, and then you plus Q, it will become 0. That explains it. So, because this graph has reflective symmetry, as we call it, because all quartics of this form have reflective symmetry, unless I'm missing something out. Anyway, so that means that C minus B is equal to A, which implies that the points are arranged symmetrically. So in 0, C, it doesn't matter where A and B, it could be here, for all we know. But what we know is that, CC cleaner, and we've got to clean that up. 0A, B, C, these two distances, 1 and 2 are exactly the same. And C must be greater than 2h. But we are now going to show that C is equal to 2h, because f of A plus f of x is always below 0. And that's why I said the quartic actually has reflectional symmetry, of course, because then Q and then the area won't be Q, then it will be Q and R, something where R is not equal to Q. So this means that C must be equal to A plus B, of course, and C is equal to 2h. Yeah, that's right. And the C equals to A plus B immediately follows from C minus B equals to A. So our expression for f of x in terms of C and x only. So since h is equal to C over 2, then big F of x equals to 1/5 x squared x minus c squared x minus c over 2. And if you do the derivative and expand and simplify, you get things like x4 minus 2cx cubed plus 6 c squared x squared over 5 minus c cubed x over 5. And show that the points of inflection y or L or x lie on the x-axis. So as you can see here, there is a maximum here. That means d over dx equals to 0. So as you can see here, 0 and 0. Now as you can see here, if there is a minimum of area x equals to a, that implies that the derivative on these points at A and B are equal to 0, and the point of inflection is usually defined as the point where d squared y over dx squared is equal to 0. That is when the derivative of the derivative equals to 0. You might have not learned this in calculus class, but well, if you do, well, that's great, and if you don't, well, it's another addition to add into your toolbox, I guess. So anyway, we had just proved that the show that points of inflection y and x lie on the x-axis, as the quintic has 4 stationary points at 0, A, B, and C. And you can prove, and once again, because the minimum of sine area is negative q at x equals to A, maximum at q of x equals to B, and then it goes back down to 0 at x equals to C. Alright, well, that was a very interesting question. See you in another step video.